I want to thank you, first of all, for joining Javelin for this webinar. My name is Shawn Bontaine. I'm going to be leading this webinar, and I'm going to be talking to you about geometric dimensioning and tolerancing. So over our short time together, I'm going to talk to you a little bit about GD&T in general. Then we're going to get into kind of some sample material from the course content from both the fundamentals and the advanced course. And then from there, we'll also take a look at kind of questions as time permits at the end. Remember that this is both courses that Javelin teaches are 12-hour courses. So this is just a real quick sampling and kind of a discussion on GD&T. So if I start off, I'm going to go ahead and turn off my video. I just want to make sure, because we are recording this, that there's lots of room on the screen and that you can go ahead and see the screen properly. So I'm just going to make a couple small adjustments here, just so that, again, everything is nice and clear. From here, just to start off, one of the things that we're doing today is we're doing this through Zoom. So just keep in mind there is a Zoom interface that you're working with, and that with the actual Zoom interface, there is a bar right at the bottom where you can mute, you can raise your hand, you can ask questions, etc. So just one thing to keep in mind with the actual, as we do the actual presentation, if you could please make sure that you are muted. That way there's no background noise coming in and you can hear me clear and concise. So there is an adjustment there for your microphone. If you do have a specific question, we'll try and hold the questions to the end. I've made sure that there's some time at the end for questions, but if there is something critical that you wanted to jump in, just unmute and ask me, or raise your hand and we can pause for a second and I'll do my best to answer your question without going too far off the rails for timeline. And as you can see, there's also chat. We do have another individual from Javelin that is monitoring the chat. So if I miss something, they can reach out to me or they can pause me. But you can raise questions in the chat. And at the end, I'll go through the chat to make sure I haven't missed anything either. There's also nonverbal communication where you can put up, raise a hand, or you can, hit a check mark, etc. So there are some nonverbal communication as well that you can do throughout the actual webinar. So just a little bit about myself. My background is my background is mechanical design. I went through as a mechanical engineering technologist at Conestoga, and I've been working for Javelin for about 10 years now, training SolidWorks and GD&T. My work experience, when I first got out of my schooling, I went into military and aerospace. Then I transferred over to automotive for a while, and then I spent some time in automation. I have my SolidWorks certification. I have my Ontario teaching certification, and I've been certified in GD&T for over 20 years with ASME. What I'd like to discuss with you today and talk to you about today is just GD&T in general. First of all, the thing I want you to realize is that drawing packages are a form of communication. Right now, I'm communicating with you verbally. When we produce a drawing or a drawing package, we're communicating as well. We're just doing it non-verbally. It's important to capture your full design intent on your drawings. You do not want to have any assumptions. You want to make sure that your drawings are clear, concise, and your design intent is properly captured. So when we look at customer prints, we'll often see customer prints that have a lot of geometric dimensioning and tolerancing on it. And it's important to be able to understand what is actually being required of you by the customer. And as you produce your own drawing packages, it's important that you communicate effectively as well, so that anybody that is either using your drawing to produce the actual part or parts, or somebody that is using it to inspect, has a clear understanding of what is required. When we think of geometric dimensioning and tolerancing, the first thing that should come into your mind is form, fit, and function. So looking at geometric dimensioning and tolerancing and why we take the time to put it on our actual drawings is, first of all, GD&T ensures that the functional requirements of the assembly are transferred down to the individual parts. So that form, fit, and function I mentioned is clearly communicated on the actual drawing. This leads to reducing scrap and rework, as now someone looking at the actual print has a true picture of what is required. That design intent is communicated. So we get better and more consistent results at the time of assembly and insertion of spare parts. In other words, when parts come in and we go to assemble them together in the machine or in the product, we have a better confidence that they are going to actually go together the first time. It also leads to a different thought process during the design stage of the parts. Designers now relate in dimension based on the relationship of mating parts, focusing on the function of the assembly and eliminating assumptions on the shop floor. Another benefit of applying geometric dimensioning and tolerancing to a drawing package is that we use universal symbols. So we get into these universal symbols like flatness, perpendicularity, profile of a surface, parallelism, etc. And instead of putting large wordy notes trying to explain function through those notes, we can now do it through feature control frames, characteristic symbols, datum references, etc. So generally, by applying geometric dimensioning and tolerancing, number one, it captures the form, fit, and function, leads to much better communication between engineering and manufacturing. It goes ahead and leads to better communication between customers and suppliers. It ensures that your parts go together right the first time and that there's no assumptions by the individuals making it. And at the same time, it also leads to those better confidence in spare parts. When you have to replace something down the road, you want to make sure that you can replace it immediately and not have extended downtime. So those are some of the reasons that we take the time to apply geometric dimensioning and tolerancing. Now, to go into geometric dimensioning and tolerancing, the first thing that we should talk about is datums. By definition, datums are theoretical exact points, axes, and planes. These elements exist within a framework of three mutually perpendicular intersecting planes known as the datum reference frame. Remember that when we assign datums, what it does is we're thinking about how we're going to immobilize the part. We want to take away those degrees of freedom, and we want to immobilize the part so that we can either make the part or inspect the part. So the purpose of that datum reference frame, it immobilizes the part, taking away the 6 degrees of freedom, 3 translational freedoms and 3 rotational freedoms, and it establishes a natural origin. We can apply datums, or first of all, datums are applied with letters. So we have our letters to identify our datums. So the datum feature identifying letter. We can use any letter of the alphabet except 3. They want you to avoid using I, O, and Q because I looks like a 1 and O and Q look like zeros. But any other letter of the alphabet could be utilized to identify your datums. Everything is referred to as a feature. We then break it down into datum surfaces, which are datum features without size, and we commonly apply datums to surfaces. They then become the locations for positioning features and locating off of to drive our dimensions. But we can also apply datums to features of size. When we apply datums to features of size, we generally select it on the basis of its geometric relationship to the toleranced part. When we're dealing with applying datums to features of size, note the datum is applied on the feature, not the feature's axes. It then applies the actual feature's axis or center plane. So you can see right on the screen here, we have a couple of examples there of applying datums to features of size. The second thing that I'd like to mention to you today, now that we've talked about datums, is to get in and talk about feature control frames. Feature control frames are a series of segments or compartments that stack together to communicate information. The important thing to remember with feature control frames is it's the order that is important. The first actual segment or compartment of a feature control frame is the actual characteristic symbol. And we're going to be talking about those different characteristic symbols in a few minutes. But the first compartment is always the characteristic symbol, whether it be flatness, straightness, perpendicularity. The second segment is the actual physical tolerance. So this is your allowable tolerance. So in this figure 6-24, we can see that we have a flatness requirement of 0.08. We can see that we have a straightness requirement of 0.04. These two fall into the context of form tolerances. Form tolerances don't reference datum. They just talk about the geometric shape of the feature, but they don't reference any datums. So in these feature control frames, we only see two segments or two compartments that make it up. When we take a look at figure 6-25, we see a feature control frame here that we have a perpendicularity, one of our orientation tolerances. We have a perpendicularity of 0.5 to datum C. In other words, we're talking about a 90-degree condition to datum C. So instead of trying to write that in a large wordy note, by using an actual feature control frame, you can effectively communicate with a lot less writing and capture your design intent. If we read the actual full feature control frame, it says that we have a perpendicularity diameter 0.05 at maximum material condition to datum reference C when it is at maximum material boundary. So again, you can come across additional things placed in feature control frames, but the normal breakdown is characteristic symbol, followed by your allowable tolerance, followed by any applicable datum references as necessary. When we also talk about those datum references, remember that it's the order that's important. The first one that always comes after the actual feature tolerance or allowable tolerance there is the actual primary datum. The second one is the secondary datum. The third one is the tertiary datum. So it's not the actual letter that goes ahead and specifies primary, secondary, or tertiary. It's the order that they appear in the feature control frame. So in this case here, the top one is ABC, the bottom one is HDG. So again, right after the allowable tolerance specified in the feature control frame, you come across your actual datum references. Another thing to point out is that coming across feature control frames on drawings, there's four main ways that you can place feature control frames on drawings. The first method is to attach the feature control frame to the actual feature callout. So in this case, we have 8 clearance holes on that large flange. And those clearance holes, then we have a positional requirement telling us the actual location of each one of those holes. So by attaching the feature control frame right to the actual feature related callout, it will then move with it in SolidWorks as you rearrange it on your drawing. Another example of doing that is for this M42 by 1.5 thread. We have the feature control frame attached right to the feature of size. As we come down, the second method is by placing a leader pointing to the actual surface or feature of size. So in this case here, we've got a flatness requirement of 0.02 to the surface. And if it meets that flatness requirement, it then qualifies or establishes it to be our datum A. Here for this internal diameter, not only do we have to produce the physical size, but we're now telling the individual that's making it or inspecting it that there's also a circular runout of 0.06 to datum A and B in order to qualify or establish this feature now as datum C. So that is the second method of applying a feature control frame, is using a leader directed callout to either the surface or the feature of size. You can also communicate or come across feature control frames. The third method is by bringing an extension line up from the actual surface where it appears as an edge or a line, and then you can attach the actual feature control frame to that extension. The fourth common method is by making an extension of the physical dimension and attaching the feature control frame to an extension of that dimension. So not only are we controlling the diameter and we're controlling the depth, but we also have a perpendicularity requirement to datum A in order to establish this feature as datum B. So as we go ahead and we apply our feature control frames to a drawing, keep in mind that we can apply them in different manners, and these are the four most common methods. Now, the current standard for geometric dimensioning and tolerancing is the ASME Y14.5-2018 standard. The previous standard to that was the 2009 standard, and before that was the 1994 standard, and before that was the 1982 standard. So as you can see, these standards don't come out every year. Unlike SolidWorks that releases every year, GD&T, the actual standard, only comes out every 10 to 14 years. So in the actual GD&T standard, in the 2018 standard, one of the main changes in that standard from the previous standard is they have dropped concentricity and symmetry from the standard. So now we just specify position instead of concentricity or symmetry. They deemed that concentricity and symmetry were redundant and could be covered alone by positional. So that is one of the changes that we discuss in the course, and we look at other changes from the 2009 standard to the 2018 standard. Another thing to keep in mind is if I take a look at the actual chart from the 2009 standard that still includes the concentricity and symmetry, this chart clearly shows how we can break GD&T down into types of tolerances. So typically we break them down into form tolerances, profile tolerances, orientation tolerances, location, and runout. Inside these types of tolerances, that's where you find those actual characteristics I was mentioning. Under the form tolerances, we have straightness, flatness, circularity, and cylindricity. Again, to try and cut down on wording on drawings, we convey these characteristics in the form of symbols that go into the feature control frame. So here you can see the corresponding symbol that lines up with the characteristic, and that becomes the first compartment or segment of your feature control frame. With the profile tolerances, we have profile of a line and profile of a surface. With orientation, there's angularity, perpendicularity, and parallelism. And with our locational tolerances, there's position, formerly concentricity and symmetry, but now just position in the 2018 standard. When we talk about our runout tolerances, we have circular runout and total runout. In the actual course, the full-blown course, that is where in the fundamentals course, we go in and we talk about all these individual tolerances in great depth. So when the form tolerances, as mentioned, straightness, flatness, circularity, or sometimes referred to as roundness, and cylindricity. Remember that our form tolerances control the geometric shape of the part feature. They specify how much the part surface can vary from perfect geometric shape, and they're not referenced to a datum. So again, there's no call out to a datum. We're talking about the actual geometric shape of the part feature. With our profile tolerances, that is where we look at profile of a line, which is 2D, and profile of a surface, that's 3D. So they specify a unified boundary along the true profile within which the elements of the surface or line must lie. So when we have our profile tolerances, we're calling back to our datums, we use something called basic dimensions that give us our theoretical perfect or true profile. We look in the feature control frame to see how much we can vary from that perfect profile. And then as long as we fall within that band, we meet our actual requirements. Under the grouping of orientation tolerances, we get into angularity, perpendicularity, and parallelism. One of the things that we stress in the actual course is we stress that the difference between orientation tolerances, and locational tolerances. And the importance of asking yourself, is it the orientation that's important, or is it the location that's important, in order to understand what is the best characteristic that meets your functional requirements. So we go through the individual characteristic symbols, and then we go into much more depth as we go further into the course itself. But for now, just for this kind of a taster of GD&T, the orientation tolerances, angularity, perpendicularity, and parallelism. And these orientations control the relationship of the part features to one another, and they are referenced to a datum. When we look at our locational tolerances, position, concentricity, and symmetry, remember that locational tolerances control the location of features to one another in respect to a datum or datums. They also talk about how much the feature could vary from a perfect location, and they are referenced to a datum or datums. The last type of tolerance are our runout tolerances. With our runout tolerances, we get into circular runout and total runout. They control the functional relationship of one or more features of a part to a datum axis, and again are referenced to a datum. So runout tolerances are a surface to axis control. We're talking about the surface of the feature compared back to the axis established by the datum. So our runout tolerance are going to give us our roundness and off-center condition. If I just go back up a slide, concentricity and position are axis to axis controls, where runout is surface to axis. So again, we get into discussing what is the actual meaning of the characteristic. Another thing that we get into in our courses is we talk about modifiers. We go through the different modifiers: maximum material condition, least material condition, and regardless of feature size. When we talk about maximum material condition, on its own, it's often referred to as MMC, but when placed on a drawing, it is an M in a circle placed in the feature control frame in the tolerance portion. So maximum material condition on its own is the condition that gives us the most amount of material or the most amount of weight. So when we're talking about an OD, it's going to be the largest OD within its own feature tolerance. And when we're talking about a hole, it is the smallest hole that's allowed within its feature tolerances. What's going to give you the most amount of material in your part? How it then relates is that when we look at the feature control frame there, we can see that it says that we have a positional requirement, diametrical tolerance zone of 0.002 at maximum material condition to A, B, and C. So what it does is it's talking about the worst case scenario. When that hole is on its smallest size, we can only allow it to be out of position 0.002 in a diametrical tolerance zone. However, when placed in a feature control frame, it goes ahead and it adds an additional tolerance or bonus tolerance at the time of manufacturing. In other words, as we depart from maximum material condition, in this case 0.495, smallest allowable hole, for every increment that we depart from that maximum material condition, we can add directly into our allowable tolerance in the feature control frame. So you can see when this hole was produced at 495, just like the feature control frame says, you're only allowed a diametrical tolerance zone of 0.002. For every increment that you measure after the actual part's been produced, for every increment away from that MMC, automatically we can add to our allowable tolerance. So the philosophy is that when this hole's on its smallest size, I can't afford it to be too far out of position. But as the hole gets larger within its allowable feature tolerance, it can float further out of position from the theoretical perfect location outlined by the basic dimensions, and you will not affect your function. So maximum material condition, very important thing to remember with MMC, is that number one, it can only be applied to a feature of size. like in this case, a physical hole. And number two, we tend to apply maximum material condition where our design intent is that we have a clearance application. That way, it only makes sense that as this gets larger, it's going to be clearance anyway, so it can shift a little bit further out of position. And then that's where we talk about something called a virtual condition, an inner boundary that the actual surface of the hole cannot cross. So we really get in and analyze the effects of maximum material condition, least material condition, and regardless of feature size when applied on physical drawings. If we look at the example here, we can see that we have 6 slots here that are being produced in the top of the part, and we have a positional requirement of 0.05 at maximum material condition to primary datum A and secondary datum B. So in this case here, even though there's one feature control frame, there's literally 6 individual tolerance bands about the theoretical perfect location of each one of these slots that the actual slot has to fall within. So we analyze the actual GD&T and communicate what it actually means on the physical drawing. This is important because if we're designing tooling or we're inspecting a natural part, we need to understand the worst case scenarios. Another thing that we get into and talk about is we talk about composite feature control frames. So we take a look at pattern locating tolerance zones and feature relating tolerance zones, the two components that make up a composite feature control frame. So we're going to get into talking about and just an individual feature control frame. We talk about segmented feature control frames, and then we look at composite feature control frames, and we can then take a look at what it actually means. So this is where we start to look at the actual GD&T that's applied in order to fully understand what is the requirement being asked of you on the actual print. And if you're the person that is applying the GD&T to your drawing packages, we take a look at how to effectively communicate your design intent. So we do touch on composite feature control frames as well, just to make sure that you have a clear understanding of what a composite feature control frame is, when to use it, and how to interpret it. Now, next level in GD&T. Everything that I've basically talked to you about so far has been related to the fundamentals course, but we also offer an advanced course, and we build on the concepts from the fundamental course. But one thing to keep in mind with GD&T is breaking down an assembly to determine, firstly, the functional datum selection, and secondly, the GD&T to actually apply to your individual parts. So we always take into consideration when we are applying GD&T is number one, to take a look first of all at the actual assembly. Okay. Sorry, a question came in here. To go to full screen. Yeah, let me just. I apologize. Now that I'm close to the end, someone finally shot me a text saying, could you please make this full screen just to make it a little bit easier to view? So I apologize for that. So when we take a look, I was just saying that whenever we take a look at applying geometric dimensioning and tolerancing, the first thing that we should always do is take a look at the actual assembly. So that, and that goes for just regular dimensioning as well. We should never start dimensioning an individual part or parts without knowing where those parts go and how they interact with the mating parts. So we always start off by taking a look at the physical assembly and thinking about how the actual part fits into that assembly. By looking at that, you now have a much better understanding of what that part actually does. And remember that when we produce a physical drawing of a part, we want to be able to communicate to the individual making it that might not have a clue where that part's going. So we have to dimension based on that. So we always look at the assembly and then we start to think about what is the functional datum selection. In other words, what are your mounting faces? How is this part going into the assembly or into the piece of equipment or machinery that it is designed for? So we look at functional datum selection and we talk about, what is the largest mating surface? From there, is it then butting up against other surfaces for things like your secondary and tertiary datums? Or are you doweling it to another part and it's being transferred through those dowels? So we talk about a kind of an order on applying datums to make sure that you are applying it based on functional datum selection. The next thing that you want to do is you want to take a look and say, okay, well, what function and relationship information should I now transfer down to this individual part in order to make sure that the person making it or inspecting it has a clear understanding of what's truly important, that form, fit, and function. And we start to ask ourselves, what is the best characteristic to apply? Is it a location that's critical, or is it an orientation? So that will help us determine whether we should be putting on a positional or a profile call out versus a parallelism or perpendicularity call out. So we want to make sure that we look at which characteristic to apply. When we talk about things like coaxial shafts or step shafts, we start to ask ourselves questions: is it a surface to axis, or surface to axis, including size control? And again, taking a look at what couple of applications on where you would choose a total runout over a positional callout. And then you can also get into applying tolerances in feature control frames. This is something else that we go into detail on, is what is the actual tolerance I should put in the feature control frame? Well, again, taking a look at what is the function and relationship we're trying to achieve. Is it also taking a look at machining achievable tolerances? What is an achievable tolerance that you can expect for a CNC to make machine to be able to hit every time? And then balancing the true function and relationship that you need to meet your design intent to what is realistic from machining and seeing how they line up. Another thing that we do is we get in and we talk about, looking at a breakdown of an assembly or assemblies where we do literally, number one, determine where are your actual functional datum selection. And number two, what features need to be tied back and what are realistic values to be in those feature control frames. The other thing that we get into is tolerance stack up in calculations, taking a look at plus or minus stack ups, looking at profile tolerance stack ups, profile tolerance assembly stacks, boundary stacks, talking about fixed fastener calculations and assembly calculations, working back from an assembly to see what are the realistic tolerances to put in the feature control frame that you can then achieve your actual end condition. So these are all things that are placed into, and let me just go into chat. Okay. Weldments and castings. Yes, we do get into, when we talk about datum reference frames and datums, we get in and we talk about looking at datum target points, partial datums. We take a look at castings and injection molded parts, discussing those. And we get into looking at, again, datum targets or partial datums when there are applicable. Also applying GD&T to certain specific areas. So from here, the actual fundamentals course, like I said, I've got limited time. This was meant as just kind of a quick overview. The complete fundamentals course takes 12 hours. It's broken down into 3 4-hour sessions. Currently, we're offering it online. They're due to COVID, but it has been done in individual companies as well. There is a complete advanced course, is 12 hours as well, broken down to 3 to 4 hour sessions. So in the fundamentals course, for example, we talk about the benefits of geometric dimensioning and tolerancing. We get into looking at the characteristic symbols. We take a look at feature control frames and datums. We get into the modifiers, looking at all the individual applications of the modifiers. We get into looking at one method of inspecting for the characteristic symbols, because nowhere in the standard does it tell you how to inspect. So we take a look at at least one method of inspecting for the characteristic symbols, which helps reinforce the actual meaning of the characteristic symbols. And we get into a little bit of a comparison of them as well, when you would choose one versus another. Then we get into taking a look at datum reference frames, where we break it down into discussing datums being applied to surfaces and features of size. We take a look at partial datums, datum target points. We look at the functional breakdown, functional datum selection, and we take a look at a little bit of applying the actual feature control frames on how many datum references are actually required. We then get into looking at composite feature control frames versus segmented feature control frames. And then with that breaks down into some exercises as well, so that it's not just me talking the entire time. So that is the actual fundamentals course. The advanced course tends to focus more on, it does a little bit of repeating of the fundamentals course to really emphasize different key points, but then it gets more into applying GD&T and tolerance stack up. I wanted to leave time for questions. Okay, so I'm just going to turn my camera back on, and I'm going to stop sharing for a moment. That is what I wanted to present to you today, just to kind of give you a feel for, number one, thinking about applying geometric dimensioning and tolerancing, as well as having a comfort zone on being able to interpret geometric dimensioning and tolerancing. I wanted to give you an idea of what Javelin covers in their 2 courses and get you thinking about the importance of applying geometric dimensioning and tolerancing to your actual physical drawing packages. And of course, now with model-based definition, you can apply it right to your physical models as well. But the course itself is more understanding GD&T and more approaches the actual applying it to the drawings. Okay. So I've got a couple of minutes now before we finish up. Is there any specific questions that you had that I can help answer or try to answer?
Well, model-based definition, I've been in discussions about that. Is there a technology in model-based definition that let me go to any shop and show them drawings? Do they have to have a specific piece of software?
What ends up happening with model-based definition, you're applying it right inside your SolidWorks models. So you are applying it to the model, so that when you send that math data over the physical models to somebody, it is attached to the models. Now, typically what you can do is you can produce PDFs of your actual model-based definition, so that you, instead of sending a drawing package, you would have a PDF of the actual drawing.
That's a 3D PDF.
Yep. So you've got, you can break it right down into saving it out as, or producing an actual PDF. So there is documentation that goes with it.
Yeah.
But the idea is to literally, as we start to move towards the concept of paperless, and we need to have some way of bringing the actual information into the actual models, so that we can tell people the importance and the accuracy, etc. So that's the concept behind model-based definition, but at the same time allowing you to produce PDFs from that model-based definition, so that you're not totally drawingless.
Well, when you say, okay, like the last well-organized place I was at used SolidWorks to create its models and drawings, and then it transferred a PDF of the drawing and a step file from the model over to purchasing, and they sent that up to the shop.
Yep. So this is a little bit.
So they were working off an actual formal drawing with very good
Yes.
quality, with very high quality GD&T on it.
Absolutely.
But if I want, if I want to send the model out and I apply GD&T all over the SolidWorks model, that will remain attached on the 3D PDF.
What it does is it remains attached to the model, right? And then at the same time, you can produce a PDF and it will be attached to the PDF.
Okay.
Okay. So again, model-based definition is something that I'm sure Javelin's sales department would love to talk to you more about and answer those questions. I just want to point out that when we apply actual GD&T, when we look at it in our courses, we focus on the actual drawings because most people are still producing drawings. But just keep in mind that through model-based definition, you can apply it to the physical models as well, and then either import them into your drawings or just create PDFs through model-based definition.
Left to my own devices, I really fanatically prefer drawings, but I've been in the discussion. I'd just like to understand, because it sounds to me like the guy can't deal with 3D models unless he's got the actual SolidWorks software. If he's a inventor shop, then he can't talk to me.
You could still send a PDF, right?
Yeah.
Created from the model-based definition. So you can, if somebody's not using SolidWorks and still needs drawings, you can still satisfy that, but you won't be completing an official drawing like you typically would in standard out-of-the-box SolidWorks.
Is there red line? Okay, most of the software supports red lining. The blue line, I find the blue highlighter is hard to do. Can you do that in 3D PDF?
That is something that I'd have to check into. I can't answer that one off the top of my head.
Like, I'm not even sure how you would implement that.
Okay, that is something that, again, further discussions with Javelin and our support people are absolutely fantastic. Mm-hmm. Okay, any other GD&T related questions? So that pretty much finishes what I was hoping to cover with you. Like I said, I just honestly, I want to encourage you to think about geometric dimensioning and tolerancing. Make sure that when you are interpreting drawings that, you able to interpret the drawing correctly. So understanding the GD&T that's being applied. And if you're the person that is applying GD&T, again, have a much better understanding of what to apply, when to apply it, and how to apply it. So that is where I think we'll wrap up then. I want to thank you all very much for joining the actual presentation today. And it's been my pleasure.
Thanks so much, Shawn.
Okay.
Thank you, Shawn. Have a good day.
Yeah, have a great day.